We have today some more speakers online. Our foreign colleagues, Domen Mongus from Maribor University, and he will be speaking about the potential in spatial development in the process of recovery of Ukraine.
Really nice to hear you. Thank you for coming.
Thank you for inviting me. I'm just okay. Thanks. Hope you can see my screen. Is everything okay, Dan? Hello. I guess it is. So I guess I can start. Yeah, my name is Domen Mongus, and I will talk today about something that we call geospatial intelligence. In general, what do we mean by geospatial intelligence is that we are dealing with the systems that capture the spatial behavior or spatial patterns of the behavior. Essentially, what we are doing is we somehow design systems that are composed of four key layers. These are monitoring layer, diagnostics layer, and prognostic and optimization layer. In a monitoring layer, we are trying to gather the data, as much data as possible from various data sources and data streams, align them in time and space in order to provide somehow a comprehensive picture of what is going on in the geospace. On top of this data, we can then implement diagnostics algorithms in terms of classifiers, feature learning algorithms, visual analytics algorithms, and stuff like that. On top of that, we can then do prognostics in terms of spatial temporal regressions, context learning, stuff like that. And of course, try to optimize everything in order to implement some kind of, let's say, optimal or close to optimal solutions into the real world. I know that this is somehow abstract, so I'll try to be, I'll try to go through a couple of projects at each of these levels in order to present what do we mean by that. At a monitoring level, for example, what we are doing currently in Eastern Africa is we are developing a system for systematic monitoring of agroecological indicators for the whole East Africa. On one hand, this includes some global indicators like greenhouse gas emissions, soil health status, organic matter, soil organic matter, crop development, and stuff like that. And these are, for example, these are the indicators that can be generated from satellite data. We then input also some socio-economic data, which is openly available, like, for example, data from United Nations, World Bank, national environmental agencies, and stuff like that. And based on that, we can then also integrate some farm specific data like water pH that they have, or nutrient composite and stuff like that. And based on that, based on this whole set of agroecological indicators, we are then designing the agroecological transition of farmers. Okay, these are often this type of comprehensive assessment or comprehensive data integration systems are often based on something that we call the data spaces. Data spaces are, now it's quite a trend to develop data spaces in all kinds of different domains. But essentially, when doing systems like that, we often, spend too much time related to data harmonization, data integration, and stuff like that. While the data space concepts allow us to integrate the data in a completely different method. In a particular, data space is more or less centered around a catalog of data sources, which are essentially only APIs APIs that allow you to, systematically find the data source wherever it might be. That means that these catalogs are composed of APIs provided by different data providers. Each of the data providers is responsible for their own data, is responsible for quality assurance of the data and stuff like that, and it only needs to provide metadata to this catalog with access rights, so that the data provider and the data user can, on the fly, on demand, decide on the means by which the data will be shared. Simply speaking, it should be computer understandable metadata, so that you can, simply write a script based on which you can search through all the available data sets at one point, negotiate the terms of the usage of that data set, and then obtain a token, and with this token go to the actual data provider and get the data from the data provider, which you then may use in your systems. Our systems are traditionally designed, in such a way that we have like tons of third-party data providers, which we access through something that we call data connectors. We can get the data, and then we usually have a backend application that allows us to produce some data products. These data products are then stored in our data distribution system and can then be redistributed to either any type of front-end applications, or it can be translated to different third-party users. Why this is efficient is, yes, because we can then try to develop all kind of AI systems or stuff like that. As for example, at a diagnostics level, we are doing quite a lot of, for example, with farming, where we are trying to, in this particular project, we are getting the data from satellites. We are getting the data from weather stations. We include soil lab testing of soil lab testing, and also IoT for water monitoring. Based on that, we can then determine the water health status, soil organic matter, and detect crops, pesticides, and diseases. And based on that, we then on one hand produce spraying maps. These are just maps, that define for each pixel how much of fertilizers or pesticides should be applied on that particular pixel, or that particular region. These spraying maps are then uploaded to the tractors, and these tractors, when they are running around and spraying things, they apply always only prescribed amount of fertilizations or pesticides on the actual region. We also produce irrigation parameters, which are then used for to optimize spraying, again providing the actual parameters of how much water should be applied on a particular region. So this is some kind of let's say a diagnostics level where we just gather the data, we just do some classifications in order to deliver some data products. When we are talking about prognostics, of course, we are trying to predict how the system or how the spatial things will evolve in the future. And in this particular case, for example, we have developed a national traffic prediction service where we integrate real-time traffic counters data. We have a dedicated system that allows us for monitoring the speeds from the actual cameras, and based on that detect traffic jams. We also integrate weather data. We also integrate holidays from the neighboring countries, and in this way, develop quite a comprehensive system for monitoring the traffic. Based on that, we can do again real-time traffic jam predictions, detections, and the predictions and the prognostics of the traveling time and traffic. In this particular case, we are doing traffic predictions for up to 1 year in order to optimize the scheduling of the activities. When we are talking about optimization, you know, then, for example, we have also developed a vegetation management system, which essentially allows, which essentially deals with LiDAR data. We also integrate soil height status, shadow maps, weather predictions, work prices, and so on. But essentially, you know, when somebody with a drone or airplane flies over the power transmission lines, it gathers 3D data about the vegetation and stuff like that. When it comes back, it imports the data into our system, and then the 3D models are automatically generated. 3D models of power transmission lines, 3D models of vegetation, and then the whole vegetation lines are inspected in order to see whether there is a tree too close to the power transmission line. This data is then also fed into the tree growth prediction system, which is tuned based on that, so we can then do the predictions for the tree growth for the next couple of years, and based on that, produce maps where there will be some critical event or where there will be some danger or hazard in the next year, and based on these inputs, we can then estimate the costs related to cleaning such power transmission line, and based on that, we can then optimize the costs and actually order work orders, which are then fed to the asset management systems of our government. So essentially, we usually address this whole range of activities, but what I was asked to particularly discuss here is a system that it's a military system that we are developing, and it is related to real-time map generation with the objective to improve military tactical capabilities. In this particular case, what we are doing is we developed a system that allows for capturing, you know, or with a drone, you know, whatever kind of a camera you have on a drone, as long as it is NATO standardized, the video stream can then be registered into our platform for real-time video processing. This video processing can then, you know, estimates or detects the particular objects that we are interested in, and produces a 3D map, which can then be distributed. Today, we are focusing our developments here into a system that will allow a rapid generation of models, which means essentially, define new detections, and try to, you know, process multiple streams at once. We are also currently in the plans of transmitting this technology to civil use. So essentially, how the system works, we have like three key components. One component is a let's say a workstation which is in charge of producing the models. Here, you know, we do all the training of object recognition models to be applied on video streams. Usually you need to have some training data for this purpose. This training data can be gathered from whatever kind of a system that we want to have. We also have a dedicated edge device which is capable of doing real-time object detection, and it is fit and it is in line with the models that we are producing, so we can directly apply a model on that one, but essentially, you use some archived video streams, which can then be used to rapidly generate a training model. This training model is then stored into the database of training models, where you can learn it a little bit more or train it a little bit more if you are not satisfied with that, or you can use this with the principles of strengths and learning to apply, or to generate models, specialized models for recognition of things and stuff like that. And then this model can then be used with a monitoring application that is usually a laptop that military uses in their tactical missions, or it can be applied on an edge device, where can be where the streams coming from drones are processed in real time, and the maps are generated based on the projections. Based on the projection of the detected objects onto the ground. These maps are then via data connectors, registered into a data space and can be distributed wherever in the world. Currently, I think we need like maybe 3 seconds to produce a map and distribute a map like this. These are some of the results of the monitoring. But currently, what we are currently support is we support STANAG 4609 standard. The current systems over the developed object recognition systems allow for processing of RGB, infrared, thermal data, and also some LiDAR data. We support currently detection of military and civil personnel, buildings and vehicles with cannons of different calibers. Generally, we divide them on small, medium, and large. We can process on a regular laptop. We can process over 20 frames per second, which essentially means that we are at least close, or if not real time. We can track over 80 objects in one time and produce a new map, as I said, in less than 3 seconds, and distribute it wherever needed. So to recap, data is more or less for all the systems. It's data more or less already available. Okay, solutions are also partially available. So the only thing we need is we are still waiting for data spaces to be somehow more standardized in order to become in order for things to become really, really fun. So thank you, and that's it from my side.